All right, so we're going to pick up where we left off during the Wednesday meeting. We had a class, not a class, but a review class on Wednesday. And I reviewed these formula that I consider new from as compared to the set of formulas that I gave you for ex post data and ex ante data in this document here. Right. And then I also had the finance notation. I also had the financial notation formulas. And then we got into, the set of notes and talked about calculating, given this information back here about two assets, combining them into a portfolio of assets. So this is the information we have about them that we need. And we calculated the mean and the standard deviation and the covariance to get the standard deviation. So these were all the steps. All right, so let's do this together. So I explain where this formula comes from. It considers the covariation of the variables. And I made a matrix and derived this formula in the general case, right? And that expression to do that, to make the matrix, is this one here on slide, I don't know what it is, slide 14. And so this basically says, use the matrix approach to get the formula. Now for two assets, we already have the formula. And it looks like that. And so we need to get, this is easy because we already have the variance. So I'll put the again. You guys hear that noise in the background, or is the sound, the noise reduction feature working here? It's a lot of noise in the background. Okay, so we need to get, using this information, I calculated the, well, let's do it again here. Unbelievable. What drives me crazy. All right. All right, so but this data, and you're told here in this example that for 50% is invested in A and 50 is invested in B. So then the weights are each 50%. And so an example, 50% of it's like if and I explained that in class, if $1,000 is invested, 500 in A and 500 in B would be 50%, right? So then we're going to basically take the average of 6 and 7. It's a weighted average, but it's essentially an average because the weights are the same. So it's so it's 6.5. And then let's get the standard deviation. So using our formula, we have this is going to be 0.5 squared. We have this, and we have these two that are just the squares of the standard deviations to give you the variance. We have this, all we need is this. So we need to calculate the covariance, and it looks menacing, but it's really just this formula here. This formula here. So we're going to enter the values to solve this. So we need to go back to the data, you see, because we have the expected returns, but we have to go back to the data. So I got to go get that too. And since the data is the weighted, we have to use the formula for ex ante returns. So essentially, even though it looks like, you know, we're using this simplified data set, when it comes to covariance, we have to go back to the basics. We have to go back to the original data set, and you know, like this one here. So we're using this formula. All right, so let's get the data and do this. So the data was back here. This is it here. You can do this in Excel, but obviously, during the test, a written test, you're gonna have to do it manually. Now, I said I never give you too many values. So I put that there. Let's put this here. And what I need to do is, I mentioned to you, just make columns. Sorry. I want to take this formula as well. Okay, so I have everything here. So we're going to make columns. There's just two observations, two weights. So it's going to be 0.4, 0.6. So I just copy that down. And then I'm going to copy this column here down here, and this column for B down here. If it helps you, you can put the zeros in so it looks more similar to the above. And then I'm going to put the columns in. I'm going to put expected return of A here and here, and expected return of B here and here. So that makes it much easier. All right. So let's do each one at a time. So I'm going to take, we're going to do this across just in brackets. So if I said 0.4, just got to be careful, bracket 0.3 minus 0.06, close the bracket, times bracket 0.2 negative, let me know if I make a mistake, minus 0.07 equals. All right, so that's the first part. So negative 0.02592. And the next one, 0.6 times bracket 0.1 negative minus 0.06, close bracket, times bracket 0.25 minus 0.07, close. So 0.01728. And when you add those together, oh, I should have stored them. That would have been good. So let's do them again and I'll store them this time. And I'll show you the data so you can see what I'm doing. Okay. So 0.4 times bracket 0.3 minus 0.06 close times bracket 0.2 negative minus 0.07 bracket equals store one, clear. And then 0.6 times bracket 0.1 negative minus 0.06 close bracket times 0.25 minus 0.07 equals store 2. So recall 1 plus recall 2 is my answer. So all we've got is the covariance. I just took the original data. Sorry. I took the original data and made columns with the data and calculated the covariance. And I get the number . Sorry, I know it's in the notes. It's over here. That wasn't good. So anyway, it's basically negative 0.0432. So what we're going to do is put that here. Just look a moment at the formula. So this is what we did. We did the deviations from the mean times each other for each variable. This notation is just telling us to go through the different states of the world. And now we have the two variances, which are just the squared standard deviations. And we're going to put them in to get this variance of the portfolio. Okay, so the only thing we didn't have was the covariance. So you have to practice making that calculation, which you would have if you did the stats review. And this is your variance. Taking the standard deviation, sorry, taking the square root gives you the standard deviation. And what do you notice? Looking back, remembering our data here, the returns, the risk, the measure of risk as the standard deviation, the measure of return as the expected return, combined into a portfolio with 50% of each, has an expected return equal to 6.5%, but a standard deviation much smaller than these. And that's because they co-vary, they're correlated. When one does poorly, the other one does well, and it's like a hedge against the downside of the other asset, and vice versa. So this results in having much more stable returns, and as a result, a lower standard deviation. Very low. This is known as diversification, and mathematically we see it as a negative covariance. If we go back to the data again, you'll see that when one is high, one set of returns are high, the other variable returns are low, like negatives. So they are negatively correlated. Doesn't have to be negative, but it just has to be low, relatively low. Everything in statistics is about means and relative measures. So this is how you compare. You compare everything to the measure of central tendency, which is the mean. So just let's peek back at the data, and you see that when A does well, B has negative returns. When A has bad returns or negative returns, B has high returns. And relatively speaking, because even though these are wild numbers, the average of A is 6%. So that's why I call this high, because it's high relative to 6%. And this is low. Sorry, this is low because it's relative to 6%. Let me know if I'm going too fast. So there's my calculation. I'm going to make another set of calculations. Oh, I see a chat comment. Oh, gracias. Okay, so the noise cancellation is very good. All right, so what next? What do we say about this? So this was one example to demonstrate to you diversification. I'm not going to talk about that because that's in the videos that I have on the platform, and it's also what we talked about on Wednesday. And what we see is that our measure 1.0122 is quite low relative to holding the security alone. If I take this is hard to look at. I need to look at this number because I'm looking at the variances now. So the variance here, we take the square root of it. So the variance is 0.00015. The standard deviation is the square root and is 1.22. This figure is smaller, just as a the variance is much smaller than if I was to just think about the average of the variances of the two. Okay, so if I just average the variance of the two of them, I would have gotten 0.03. Putting them together in a portfolio to realize their returns is much more stable in returns, right? Less volatile. So combining assets A and B into a portfolio P, we eliminate some risk. Not all the risk in this case. There is a little bit, the 1%, 1.22 in standard deviation, or this amount in the variance. And this is the result of the covariance term being negative. This is known as diversification, which is a strategy designed to reduce the risk by spreading the portfolio across many investments. In general, there's two types of risks. There's the risk that can be diversified away. It's known as unsystematic risk or asset-specific risk or unique risk. So we did quite well with those two securities. But there's also, if you look at, so financial economists have looked at this issue and noticed that there's only so much you can do by combining assets. There's still remaining volatility attributable to market risks. So as a result, we focus on the relationship between an asset returns and its correlation with market returns, right? So just to say a last few words about just combining assets. So taking this and extrapolating, like saying, okay, well, we just put two assets together and we got rid of a lot of risk. What if we don't even use any logic? We just randomly pick assets. On average, what will happen? So if I just every day randomly picked a bunch of securities, how would I do on average from day to day to day? This question was looked at in terms of what would be the risk associated with that strategy. So this was done, and this was done in the 70s, but it's been replicated since. But this is like a seminal paper. Like this is a publication that is like one of the first. All right, and it got a lot of attention. All right, so what they did was they randomly selected from a list of risky assets, so stock returns. They picked stocks randomly, and they picked one at a time. And it's like in an Excel spreadsheet, let's say. They didn't have Excel in the 70s, but they made a database, and they had, the returns to the asset they picked. And first they did, okay, this is going to look not the way I want it to, but okay. So the sample size was 1, they just went and they picked one asset, right? And they recorded its return. So they'd say like, if that was a 5% return, and remember what are returns? Go back and look, how did we calculate returns for stock? We had that formula that we talked about. So returns were computed with time series data, historical data. They might have even used ex-ante data, but I'm not sure. Probably just historical. And then, so these are all different stocks. They just randomly picked a bunch of them. And they did this. How many samples? So these are all separate samples. Oh, let's do that. Let's do that. So we're going to call this the sample. This would be sample 1. This would be sample 2. This would be sample 3. I should do it in black. 1, 2, 3, 4. So they did this for theoretically all possible samples. And then they picked, so they would have resulted in a different asset each time. And then what they did was calculated the average and then the standard deviation. For all these different samples. And this is the average annual standard deviation from doing this. Okay. And they got 49.2. So that's just using one security. That's quite high, right? Then they did like 2 securities and 3 securities at a time. So what did that look like? That looked like, so N equals 5, let's say. So they would take 5 assets and record their returns. So 3%, 18%, 5%, -2%, and 1%, let's say. So those are 5 assets. And then they repeated that. Okay, so they did that 5, and then they got averages from here, from each one, and then they got the average of the average. And the standard deviation, they calculated as the average standard deviation from all of these different standard deviations. Trying to help you understand this so I don't have to talk about it again. So from here you get X bar for each one. And what's plotted here is the average of the annual standard deviation. So these were all annual returns. And however they were calculated, in the way we understand, we calculate returns, then they calculated the annual average. And they found out that if they took 2 or 3 or 4 or 5 or 10 or 20, the S was smaller each time. So this was very interesting. The more in the sample, they were actually able to steadily reduce the standard deviation of the portfolio of assets combined. But only to a point. They weren't able, it plateaued. They weren't able to do better than 19.2%. So they referred to the amount that they could reduce as diversifiable or non-systematic risk, and the one that they can't as a systematic risk. So it matters. At some point, and this is the point about doing this randomly, it almost doesn't even matter that they pick them logically or they use some rationale. They were just randomly selected. Okay, so you could even do better if you had some sort of logic in picking assets. Possibly, on average, just picking, you're going to do quite well in reducing risk. That's the point of this. Okay. But there still remains this non-diversifiable risk, whatever the case. And they explain that by on average, it just won't go lower than this. So there's this 19% that they're going to refer to as systematic risk. So what does this mean? Okay, just to recap, total risk is diversifiable risk that you can diversify away and market risk. We assume that diversification is costless. Like, so like they just chose randomly. So there was no cost of analysis and collecting data and monitoring and doing fundamental analysis. They didn't do any of that. They just randomly chose stock with historical data or with data that they had. They didn't put any effort into computing or estimating the best portfolio. So thus diversifiable non-systematic risk is irrelevant. So in other words, you can just pick a lot of stock and you're on average you're going to do the best you can with reducing the diversifiable risk. Investors should then only be concerned with non-diversifiable risk or market risk. And market risk is measured by the beta. The beta is the slope of the relationship between the market returns and the stock returns. So this looks familiar. So this is what I talked about. I got you to the place where we looked at variables like this. S&P 500 returns represent a proxy for market returns. So the market performance, state of the economy, or return on to risky assets in a well-diversified portfolio. So I say well, but it's a well-diversified because we pick the top 500 performing stocks at any point in time. And these are the returns to a company, BCE corporation. So let's get the slope. Now this looks different than what I was talking about. This is actually simpler. It's just two observations. So when there are just two observations, it's pretty easy to get a slope. You can just do the rise over the run, right? But in statistics, there's a lot of data around, and we use the least squares prediction line to find the best fit that's closest, the linear relationship that's closest to all the points. But right now I just gave you two observations and it won't let me erase. It won't let me erase. There we go. So we only have two, so it's simple to just get the basic slope with two observations, and that's what I do here. And show you that the change in Y is I'm going to go, this is in the first one, and this is the second one. So that's 26% plus 4%, which is 30%. And the change in X going from here to here, 18 minus 6 is 12%. So the slope so this is different than I did before because it's simpler. There's only two observations, so I can do it like this. Otherwise, I have to use my formula, right? This is not meant to confuse you. It's just meant to connect, just to get the number so we can interpret it. So this ends up being 30 over 12, which is 2.5. Now we don't write a percent. This is an index. The interpretation, we make a regular slope interpretation. So how do we do that? So a 1 unit change in X results in a beta unit change in Y. I'm going to say increase. We could say decrease as well, but I'm going to say increase. 1 unit increase in X, Y increases. That's the slope. So in terms of the variables, following a positive 1% change in the market return, the return on BCE will change by 2.5%. However, we could also look at that in the negative. A negative 1%, so a loss of 1% in market return, results in a BCE change of negative 2.5% return. So in that sense, we say that BCE returns are sensitive to market returns. So we write it like this. We always put the market returns on the X and the BCE returns on BCE or firm returns I on the Y. And we are insinuating that the state of the economy influences the returns to any firm. And we capture that in a measure of the beta. Now, this is not a great or reliable beta because we only have 2 observations, but it was just to make this calculation quickly to make the point of how to interpret the slope. So from our formulas, we know that if we have a scatter plot of data, or from how am I going to say this? Given a lot more data and a scatter plot, beta is calculated as R SY over SX, or I use the symbol, the correlation times sigma. The Y is I and the X is M. But if you're thinking of them as Y and X helps you, just stick with that. This is just in terms of the notation that I introduced for finance. And assuming that this is all the data or the best set of data we have, or a distribution of data. All right. Okay, so the market portfolio we're going to introduce so the idea of the market portfolio, right? The S&P 500 is a proxy. It's a portfolio of all assets in the economy. So theoretically, this is how we're going to refer to the market portfolio. A portfolio of all assets. So every asset that has been combined to create an index. So like we could get an expected return as a weighted average of the proportional contribution of each firm according to what they represent in total market capitalization. So for company A, if they are a large company and they represent the value of their stock represents 2% of all the value in the stock market, then their weight would be the 2%, like 0.02. And that would go into an index with other assets to make the expected return and the standard deviation of that market portfolio. So I just talked about 2, but theoretically you can talk about thousands. The S&P 500 is used in practice as a broad stock market index with 500 companies only, and they create with the top 500 companies that change, they fluctuate or they change as companies close through time. You have a different set of 500. This is used to represent the market returns in my examples. So beta is a sensitivity of stock returns to the return on the market portfolio, right? So that's how we're going to talk about its sensitivity. You understand it as the change in Y over change in X. And this, what I told you here, for an additional or marginal effect, for an additional unit increase in X, Y increases by the B, the slope. And then there's this other form of the formula, which by substituting this, which is just the covariance, into here, it reduces to this because I showed you guys last Friday that the i's will cancel and you'll just get this. So this is our basic understanding of the result for 2 variables and the slope term between them. If you have more variables, calculating the beta, I haven't done that for more variables, but it's doable. The result of the trying to find the least squares regression result gives you actually a matrix, not just a single value. Anyway, we won't get into that because we're not doing that in this class, but this is equivalent to what you would do for larger, or sorry, for more assets combined. We're looking at one asset at a time, okay, and what we're doing in this model. So we're not even going there. All we're always doing is the market returns with one asset. All right, so we don't have to get into that. It's not part of this model. Okay, so let's take these results and jump into Markowitz portfolio theory. We saw that combining stocks into portfolios can reduce standard deviation. Covariance or correlation coefficient make this possible. The standard deviation of a portfolio is computed like this. All this stuff should look familiar, maybe still make you uncomfortable, but it looks familiar. We understand this. Now I've converted. I am not looking at I and M right now, but I could do all of this for combining the market portfolio and an asset at a time, but I notice I'm using A and B, right? A and B. So these were I and M, but I could do the same for those. So A and B, I can get the standard deviation, I can get the correlation, I can get, I can write this, in other words, in another way by making the substitution. So why would I do that? Well, I might not have information on the covariance. Often people just use or calculate the correlation. And so this might be more useful. So what I'm going to do now is teach you the logic behind the capital asset pricing model. And I'm going to use the formula for standard deviation or our measure of risk with the correlation coefficient, because this is very meaningful. Remember, the correlation coefficient, or a correlation in general, is between -1 and 1, and we know what that means. It's between -1 and 1. And if it's -1, then the assets A and B are perfectly negatively correlated. Well, how does that affect things? We'll talk about that. If it's 1, they're perfectly positively correlated. Well, how does that affect things? And what if correlation is 0? So I'm going to look at those 3 cases: -1 correlation, +1, and 0 correlation. But the other kind of relationships between assets will be in between those. You'll see. I'm going to show you the bounded results, and stay with me on looking at these as being a key relationships that we want to explore. All right, so I'm going to use this form of the standard deviation for risk. I'm going to introduce 2 assets where I've already calculated Y's expected return and its standard deviation, and Z expected return and its standard deviation. And there again, there's the trade-off. The higher return asset also has the higher risk associated. So we have that trade-off. And what I want to do is we're going to talk a little bit about, so when I was explaining the random selection of stock and putting them into a portfolio, well, what if you did want to consider how, you wanted to consider combining these assets together and how best to combine them, right? So I don't want to just pick randomly a bunch of them. I want to think about, well, let's think about this more carefully. How much, if I'm going to invest some money, how much should I invest in Y and Z? We're going to take 2 at a time. And then I'm going to talk about the general case. So I'm going to plot these on a graph, on a chart, and I'm going to put return on the Y-axis and risk on the X-axis. And that's here. So here I have, I'll wait for you to catch up if you're following along. So as I promised, I'm going to combine assets Z and Y, and I have risk here and return here. And it demonstrates the trade-off where as I go from Z and to considering Y, the return goes up, but also the risk goes up. Now, the Z is lower risk, but lower return. Y is high risk, high return. What will happen if I put them together in a portfolio, and which alternatives, which combinations should I choose? That's what we're going to talk. I'm going to talk about how I generate all these numbers here. Here is the formula. So I'm just leaving it as a formula for the expected return of a portfolio with this weight for Y and this weight for Z. And then I'm also going to calculate a general formula for standard deviation for this weight of Y and this weight of Z, and then it affects the covariance term as well. Okay, are we good? Tell me you're okay. Didn't lose you. So it's the same formulas like we calculated before, but I'm not giving you the weights. The weight is our variable to choose. It's up to us. So if I allow, and so Markowitz did this. Okay, so he gets credit. If I allow the weights to vary, and I consider, let's say I also left this unknown. So I'm really making this general. I'm just giving you some numbers for mean and standard deviation. But in terms of the relationship, I'm also allowing the relationship between them. So the correlation between them and the weights allowed to vary. Now, I don't choose the correlation. That's going to be given. In reality, I don't get to choose that. So although, oh no, I'll put it on the next page. So although correlation is not my choice, I have to suck up what the, I have to live with what the correlation is. I get to choose the weights. So you see here, I'm going to say the correlation is given. But let's consider these different options for weights. And I could have more. I could have put more. I could have said, like, 4, 5, 6 different weight combinations. Now the first one, let's look at the first one. The first one is across here. And this says, put 75% of the investment towards Y and 25% towards Z. So if you do that, you can go back over here, and all you needed were the weights for this. You could calculate the expected return and you would get 18.6%. So this is the highest expected return. It has mostly the high risk asset in it, right? So it has the high risk asset. So it's going to be closer. So let's use some colors. So it's going to be closer to here, like, so that's going to be 75%. I'm just drawing it on. Oh no, actually I have it marked. So why am I doing that? Let's see, what is it marked as? It's 18.6%. So that's here. So 18.6 is here. So this is going to be it. Okay, let me just say to you, it's 18.6 here. It's 18.6 here, and it's 18.6 here. So you see, there's 3 different places where it's 18.6. Let me draw that across. I'll put the dots on. I'll do blue and then red and then I hope my numbers didn't get messed up, but okay. So I'm going to do 7.6. Okay, that's the easiest one to see. Red. Okay, let's look at the red. This is 18.6 is the expected return, and 7.69 is the standard deviation. So that's here. Okay. So I'll use red for that. So this was calculated. Well, let me do the blue then. Okay, so then the blue one is okay. Okay. So the blue one is this one. No, can't be. It's this one. No, that's right. Sorry. I'm thinking backwards. So this one would be the blue one, and then the one in between I'll call the yellow one. You can see it there. All right, so the blue one is this one here. So the red one corresponds to the correlation being equal to 0. So there's no correlation between the assets. The blue one is where the correlation is -1, and you see this happening. What's happening here? How can you describe this? According to my chart here, for the blue one, it's 7.38%. So what about what is this thing? How do you describe that? It looks like, so what's happening is these are all the combinations between Y and Z where correlation is perfect. The correlation between Y and Z is perfect. It means that there's a combination of Y and Z that can completely eliminate risk. This is where risk is 0. Now, how likely is it that two assets will be perfectly negatively correlated? It's very unlikely. Okay, it's possible, but it's highly improbable. We would be interested in knowing this, and you can actually calculate that one in the case that assets are perfectly negatively correlated. So what did we do? I showed you that we can combine Y and Z with more of Y in it. So more of the risky asset. So this is a riskier. Because it has more of the risky one in it. And that puts you over here, and over here. So the expected return doesn't change. What does change is the risk, because that formula here depends, the formula for standard deviation depends on the weights and the correlation. So I'm going to take this away. And put it here. I mean, it's really should go up there, but it doesn't fit up there. Right. So these, the calculation for standard deviation depends what this is. So this is for -1, this is for +1 correlation, and this is for no correlation. So this one was 738, this one's 769, and this one is 798. This is going to be the highest risk. So you get my first row? Do you follow? So the formula for calculating the expected return of the portfolio, all it needs are the weights. So I calculate that, and then I consider the standard deviation, and it depends on the correlation. This one, correlation is -1. This one, correlation is 0. And this one, correlation is 1. And what happens is that there's higher risk because the lowest risk one diversifies away the risk. Okay, so if they are perfectly negatively correlated, you're able to diversify the risk and get lower risk. Can't do that if there's no correlation, just 0, but it will wipe out that extra term. Remember the extra term in the formula. If this is 0, this disappears. But if this correlation is a positive, it adds to the risk, right? So that's why you end up here. Not that much in this case, but the nature of the weights. So we could do the next set as well. And that would just be because there's less of the risky one on it, it has less return. So we would go with 7.2% would be the expected return, and you see the same pattern. As they are less negatively correlated, they go up in risk. Well, sorry, this is a bad, I should probably have that in that column so you can see it steadily rise, but anyway, it should steadily go up, just like the pattern does here. So this would be the blue one. This would be the red one, and the yellow one here. Looking at the numbers, oh, this is supposed to be 2.72%. Make it hit right on. So, 17.2. My numbers are off. It should be, I remember this graph got a little distorted. So where are those numbers? 5.16. Okay, there it is. All right, so if you put this into, it's probably easiest in Excel to put all these numbers in. But for 17.2, with a correlation of -1, this number, I could check it later. This one should be, okay, so then 5.16 is the next one, the red. And then 5.72 should be this one. Looks like it works. So let's do that. Let's calculate. Let's check for practice. So that's 5.72. That's not a very good. A bit higher up here. It's messy. So this is 5.72 in terms of risk. So the number we should check is this one. Let's try that. So let's find this. Determine what the risk is. So it's going to be perfectly negative correlation in this formula. This is -1. The weights are here. And that's it. So, and then take the square root. So you're going to put oh, sorry. The weight. So then the second portfolio has weights 50-50. So we have the new set of weights. That's what 17.2%. I didn't mention that, but so this is the second set of portfolio with 50% Y. You can see that because it's closer towards Z, right? So this combination is closer towards Z. This is actually 50-50. This one is 50-50 as well. And this one is 50-50 as well. So we'd have to put 0.5 in here. And what number do you get? My chart piece, it might be just my chart is really off scale. And that should be 4.52. 2.72 is meant to represent this one. Yeah, I know at some point in editing a Word, some version affected my chart. But anyway, that number should be 4.52, and I have to fix my drawing. But 0.5 square times 0.015 times plus 0.000144 times 0.5 square plus 2. It's not going to work. I have to do it in steps. Okay, so I just did it in pieces. Okay, what I get is this is 0.002625. And then this is 0.0003 36. And the last piece is negative 0.025617. Now put all those together. So recall 1 plus recall 2 plus recall 3. Oh, that didn't work. I think I forgot something. Do this again. 2 times 0, 2. Okay, that's that. How are you guys doing? Are you making calculations or are you waiting for me? I want you to practice because that was the point, right? We wanted to practice using this variance formula. There must be something wrong with the code. No, what is this? Is formula should be. Oh, I see why, because I've already calculated. Gee, that's what it is. So I don't need that. That's already in there. That's already done. All I have to do is change. So this has already been calculated. Oh, I don't know. So that's my typo here. Because I've already calculated this part. All I have to put in. So this was the sigma y, sigma x. Sigma y, sigma x is, wow, I actually have an error here. I didn't realize. So this is just sigma y. I had to put the sigma x in and that will fix everything. Actually, I never did this before. So this is sigma y. I have to fix this. Sigma z. So we still have to multiply. This is a typo. This should be 0.10247 times, put a bracket, 0.012. And then it'll work. 0.10247 times 0.012 times 2 times 0.5 squared. And then we get a nice number. Needs to be nice, needs to be smaller than the other ones. Okay, have I lost you guys? Are you there? So all I did was I forgot in here, there's the extra term. Of the standard deviation of z, 0.012. One more time. So 2 times 0.10247 times 0.012 times 0.5 squared times 1 negative is a negative of this. That's the whole point. And then store 3, so recall 1 plus recall 2 plus recall 3. So this is easily done in Excel, which I'm not doing, but you could. And then you take the square root. So this is all equal to 0.0020418, and then square root. Well, this is the right number. So my it's just my graph is really bad, my chart. So that should be 452. It's just a bad drawing. At some point, I know I remember my lines moved, but it works. Questions? So all that happened is that I did not write this extra term here so that you can use it here. I don't think I need to. You want to have all the annotations? I didn't do that many annotations, did I? You know, you guys are supposed to watch the videos and make your own annotations, but yeah, I guess I can upload it if I remember. If I remember, that's not the best. But I will make a note that this is wrong, but it doesn't change anything really. It's just, I was just trying to calculate these with you and it would make you crazy. It's not going to add up. So basically, it's just my scale is not good. And this doesn't line up. So in this description, I probably just had to show you this one for correlation equals -1, this one for correlation equals 0, and this one for correlation equals +1. It'll be fine, but the numbers add up. These are all correct. It's just that I missed this term here. Make a note here. So then the point of this drawing is to show you that for correlation equals -1, you can completely diversify away risk. And you could find this set of weights to do that. And the way you do it is you would take this formula and set the formula to 0 and solve for the weights. You can actually do that. This is called the minimum variance portfolio. Okay, and you could theoretically, and I've done it with other classes, where you apply this formula. I tell you this is -1, and you can solve because you have two equations. You have this equation and you have a second equation. Do you know what the second equation is? If we know this, the second equation is that the weights must sum to 1. So then you have two equations and two unknowns, this one and this one, and you can solve. So we could solve for this. Actually, you could solve for anyone because I can say, well, I want a standard deviation. I want a risk of 5. So if 5.16. If I want a risk of 5.16 and the correlation is perfectly negative, I could find it. And this would be my return. I could find the weights. I could find the return. If I set this number. All right. So what does this do? So in summary, so you could do a lot here, and this is all programmable. It's all doable. If you guys had a weekend, you could put it all into Excel and do this if you had to, if your life depended on it or a test depended on it. But in general, you're going to always get this shape. If two assets, a risky one relative to a less risky one, were plotted with the measure of risk here and the measure of return here. The one with negative correlation would be all the way back to completely diversify risk. The one with perfectly positive correlation would have the highest risk. In general, because those are the extremes, we visualize all possible combinations of assets on this curved line, this curve. Okay, so now we have to talk about, given that's the case for two assets, let's summarize where we're at. The expected returns on this axis, the standard deviation of returns are on the horizontal axis. I have this is my shape in general that I'll see, because assets are not perfectly negatively or perfectly positively correlated. It's somewhere in between. So all possible combinations are here, but we need to talk about something from the minimum variance portfolio. From the minimum variance portfolio all the way up, we refer to this as the efficient set. Okay, this is known as the efficient set, whereas the ones below are the feasible, sorry, the ones, including the ones below, is known as the feasible set. So between the less risky and the more risky asset, this is the entire feasible set. So what's the difference? What is the deal with these here? Well, these assets in here have both low risk. They're with the low risk asset. But as I move from here, so let me just show you my positions. So if I'm invested 100%, that represents 100% investment in Z. Here I've marked, this is like 75% in Z, but 25% in Y. Okay, so it's closer to Z. As I include more of the risky assets, you see here, like this asset here, this is a lower risk and higher return asset. So that does not have the trade-off feature, right? It's lower risk and higher return. I like both of those. I keep going. I'm going to put more of Y. So I'm not going to do 100% Z, because putting more of Y in still gives me high return with less risk. So keep on adding Y until here. And that's why I really like to know how to find that. And I showed you how. What did I say? You can take the, well, in this case, this one is locatable precisely here when you know the standard deviation. You know here for assets that have perfectly negative correlation, you could find this. But in this case, we don't have that, right? This is the general case. So we would actually have to put a standard deviation in our formula and estimate. But anyway, so right here, you can use calculus to find it, but I'm not going to use calculus in this course at this point, but you could use calculus to find this. Do you see how you do that? You take your equation for standard deviation and you take the first derivative and solve for the weights. You can do it. All right, but we're not going to do it. So up to here, investors will add, every rational investor will add Y up until here. Beyond here is your choice. So this is your choice set, or your efficient set. So investors, so rational investors, choose along that. They choose among these combinations, okay? That's known as the efficient set. So none of these are feasible. Oh, they're feasible. Sorry, they're not efficient. They're all feasible. I can calculate weights for them. I'm going to call these not rational. Because by adding more of Y, you can always do better and there's no trade-off. So what we're really headed for is considering the market portfolio of all risky assets. If we're to think about the market portfolio of all risky assets, we have to think about more assets. So we just looked at the two asset case. And what happens if you have more? Now, this is a multidimensional concept here that's been simplified by the theory. Oh, sorry, I'm just reading your chat. Yeah, I'm gonna put this Zoom up for sure. Yeah, I'm gonna upload the Zoom and I can put these notes. It's just that I might forget because I have a lot of things to do today. I'll try and do it right after class, but anyway, the Zoom will go up. Okay, so these are two at a time. What I have here are considering two assets at a time and on the same space, return and risk space. And now the feasible set is all combinations, because you could just, you might just choose two, right? Or you're going to change you're going to choose a combination of many assets. The feasible set is on this curve here and inside here. So these are all the possible combinations that make a portfolio. So along here, this is going to along here, many assets, they could like not overlap, but I guess they're going to have some places where they're coincident, right? Where these combinations conclude more than two. It can include many. And in fact, what's really of interest to me is those at the most outer frontier, because they have the highest return out of the ones below them. And I'm particularly interested in the high return, but also that they're more to the left than any of the ones below them or within it. So this is now a set known as the efficient frontier that includes portfolio of many assets. We assume investors are rational and they prefer more to less. They are also risk averse. So their goal is going to be to move up and to the left. Up because they like return, and to the left because they don't like risk. So if you're looking at a set of assets, you're going to do the same. And if you're plotting them in this risk return space, you're going to do the same. Looking up and to the left, putting yourself here. If you have assets in a what is the word I'm looking for? In a plane like this, you're going to choose the assets that are up and to the left, low risk and high return. So, for example, I'm gonna put names on these. So is D, so which of these assets dominate the others? Which asset dominates the others? In other words, which one are up and to the left? Now, the way that I've drawn it, I've shown you, I'm just showing you how you think about it for B. B falls here. Okay, so B is dominated by those C and D. Because C and D are up and to the left. Which dominate A? So I have to make the same sort of through A. So D dominates A. So you're just drawing through to create like an axis and looking which one is up and to the left. So D dominates A. Or I'll say it the way I did above. A is dominated by B. By D. Okay, any questions? What else? C is dominated by D. And that's it. I guess C is dominated by D.
Sure.
Yes.
Are we still going to meet on Wednesday at 6 in the campus?
Yeah. Yes, sure. I think I didn't write it about it, did I? But I said that last time we met, Wednesday. Yeah.
Yeah, because we talked about it, but since you didn't send it on email or anything,
Yeah,
some
yeah,
people in the chat were like unsure. So I guess
yeah.
making sure.
Yeah, I'll send an email about it, sure. Yes.
Okay, thank you.
Okay, thank you. Okay, you ready for the next part? Was that easy enough? Up and to the left, up and to the left. So that's the rule. Okay, so what we're going to do next, so we've talked about all possible combinations of two assets, how they depend on the correlation between them, and the general depiction of all possible combinations of two assets that investors can choose between. And their choices will begin here at the minimum variance all the way up. Otherwise, all the ones below are dominated, right, by the minimum variance and all the subsequent ones. And then I said, let's think about all assets. So they have the same shape when you think about two, but now we're going to pool them. We're going to look at all of them at the same time. And what we see is, as long as they fall in combination up and to the left, we could hold many assets at once. And this is a very simplistic way to show you something that is actually multidimensional, because you're putting many assets together, but we end up in this space. The results of the return and risk end up back in this this space. So what we're going to do, this is the risky assets. We're talking about stock returns, right? Or stock. What we said before, that investors will hold the riskless T-bill. All rational investors will try and beat inflation and hold the riskless T-bill. And to be incentivized, I explained, to hold risky assets, they have to be guaranteed a higher return. So they expect or require a higher rate of return. So let's look at the combination now. Let's look at the position of an investor holding both a risk-free T-bill and the risky portfolio, market portfolio. But to do that, I have to introduce or reintroduce short selling. What is short selling? Short selling is borrowing from a broker an asset. So you won't own the asset, but you're going to borrow it and you're going to sell it in the market and use the proceeds for investing. And then at a later date that's been prearranged, you're going to purchase the asset in the market and return it to the broker. And in practice, you know, shorting is used when someone feels or has a sense or information that either an asset's going to do poorly in the future and the stock price will drop. So when they return it to the broker, it'll be at a reduced rate, reduced price. So in the interim, they made a profit, right? A positive payout. So what about doing this with T-bills? Let's see. So let's just review short selling. So the definition is the sale of a security that the investor does not own. How is it done? It's borrowed from a broker and then sold in the open market. What cash flows do we see? At the initiation of the short sale, only your only cash flow is proceeds from selling the security because you didn't pay for it, right? You may have an arrangement with a broker, and we're not including here, we simplified away the fees, but there could be a nominal fee. It would say it's small, but not worth worrying about because you have an arrangement with your broker in general. So closing the short, eventually you will have to buy the security back in order to return it to the broker. What happens at the end? So at the elimination of the short sale, your only cash flow is the price you have to pay for the security in the open market. And in the interim between selling it and paying for the security to return it, you may realize a positive payout if circumstances change. So in this case, I'm not changing circumstances. It's just going to be as is. The fact is, here we start with a T-bill. 0 coupon, issued by the government, 3 months or 6 months, or and it has a face value of 100, which we usually work with 1,000, but I simplified it for the numbers, and with a maturity no longer than 1 year. Okay, so this one is less than a year. If the yield on a 1-year T-bill is 5%, then its current price is $95.24. So you remember this from this is a basic time value of money calculation, no coupons. That's what you pay for it. That's what people are paying for it, but you borrowed it, right? Through a short sale. So you borrowed it and you were able to sell it for the $95.24. So at the initiation, you have $95.24 if you did such a thing. So then at the end of the year, you're going to buy back the T-bill in the market just an instant before it matures in order to return it to the broker. The price you have to pay for the T-bill in the open market an instant before maturity is the $100. So it's just the face value. So nothing changed here. There was no price drop, nothing. It's just basic short sell. And I'll tell you what we do with those proceeds in a moment. This transaction is equivalent to borrowing $95.24 for 1 year and paying back $100 in a year. So that's the 5% interest you paid. That's kind of review, but I'm going to use this now here. I've plotted onto our portfolio axis, our coordinates axis. There it is right here. So I'm going to put a red dot on it. And this is a drawing of all possible portfolios. Remembering this would be the efficient one, this outer envelope. And we're going to consider a combination, a linear combination between the portfolio that's just tangential to this line with the risk-free portfolio, the T-bills. And what are we doing there? We are expanding our possibilities here because we move from being on this edge in these combinations to now being on this line called the capital market line. So on this line, we have the market portfolio. Investors invested 100% in the market portfolio are here. Investors invested 100% in T-bills are here. But there are investors that are partially invested in the riskless T-bills and partially invested in the market portfolio. So what they're doing here is they are loaning their money away by buying a T-bill and then realizing the return later. So they're combining lending, risk-free lending, and the market portfolio. That's their investment choice. So A is an example of that. Okay, so they're lending money through the risk-free rate and they hold the market portfolio. But then there's this. So this even expands the possibilities more, and the trade-off exists. Yes, they're going to get a higher return, but they have to be prepared for the higher risk. But it's possible. So how did they get here? They get here by short selling T-bill and using the proceeds, right? That $95 and 24 cents, they put it towards the market portfolio. And they can realize a greater investment because the return on the market portfolio is much higher than the average return on the T-bill. So our examples along here are investing in both the T-bill and the market portfolio, and these beyond the market portfolio are risk-free borrowing, because T-bills are risk-free, remember? Risk-free borrowing through short selling the T-bill. All right, so any questions so far? Are you guys blown away? Is this simple? So we went from portfolio theory, and from portfolio theory, we will derive the capital asset pricing model. Remembering all the assumptions that I've made here, risk-free borrowing and lending, and then, diversification has no transaction costs, and all those assumptions I've made so far to get here, they are going to be part of the assumptions of the capital asset pricing model. The capital asset pricing model takes us from risk as the standard deviation of the portfolio and expected return of the portfolio to looking at each asset in turn. And we come up with this. So what are we doing? It's a pricing model, but price when we talk about stock, remember the more basic valuation formula was like this. Our goal in Unit 5 is to actually find I. That's what we're doing. Okay, we're trying to find the required rate of return for this firm or these firms. And in so doing, we're finding the required rate of return of investors in the firm, in their stock. So think about this in the background, and our goal is to get this, and we're going to do it this way. We are going to say that the expected return to a risky asset is an adjustment over and above the risk-free rate for every unit of risk or sensitivity as measured as by the beta. We compensate by what's called the market portfolio. What is the market portfolio? Well, remember, I'm sorry, the market risk premium, not the market portfolio, the market risk premium. This is called the market risk premium. What is the market risk premium? Well, remember the risk premium from the previous unit. Not unit, the previous set of notes. I don't want to call it unit. I did it like this, right? That's how we calculated it. But now I'm going to use the general market portfolio return and refer to the market risk premium. So on average, this is giving you an idea of overall, they should be compensated for every unit of risk by the market risk premium. So this should be my required rate of return according to capital asset pricing model. So let's review some of these things. So all securities are in the market portfolio. That's what we're going to assume. We're going to assume that where this touches, this picks a portfolio that includes all risky assets in some combination. Like some could be included that have like a 0.000001% weight, okay? And some could have a higher weight. And they're all combined in there. All investors have the market portfolio in their portfolios, since they are all on the new efficient frontier of the CML, investing both in the risk-free and the market portfolio. So therefore, investors are only concerned with the expected return on the market portfolio and its risk, and with the contribution of each security I to the market portfolio in terms of the systematic risk as measured by beta. So there is a relationship between the asset and the market portfolio. By including this additional portfolio in the market portfolio, we're adding some risk as measured by the beta. And investors are concerned with the expected return. Okay, so we're going to use this formula. This is the capital asset pricing model. These are formulas we've already seen, remembering that the beta, and so you practice this if you had a chance, hope that the beta of the market portfolio is 1. Because what is the beta? Beta is the sensitivity of stock returns to the market returns. That's what would be measured here. But what if I have the sensitivity of market returns to market returns? Well, that would make, if I was to graph that, all the data would be perfect on a line, and it would go like exactly like that if I did that. So the beta of that, the slope of that will be 1. So this would be, oops. So yeah, got it? So let's plot in a new coordinate plane. We're going to look at risk and return, but for the asset. So that's what I have here. The risk of the asset in terms of the beta of the asset. This is our measure of risk, and this is our measure of return. And here we have the capital asset pricing model. All assets in the market, given our assumptions and the theory, will fall on the capital asset, will fall on the security market line, it's called. This is the capital asset pricing model, that line, which we called it SML. Okay, so I have a question for you. What is the slope of that line? What is the slope of that line? The slope of that, no, that was the slope of this line was 1. But that's not what I'm marking here. So you got to be clear about your axis, right? But no, that was the slope of this one here was 1. But this is a different axis. And this line is this equation. So what's the slope? Okay, so it cannot be beta because beta is not the slope. Beta is the x-axis. So it must be the other thing. So first, let's go through this in terms of a line. So this is the y-intercept. This is the A. This, so this is the y-intercept here. And this is the, not the slope, right? Because this is the x. This is like the x. So it means that this term must be the B. So this term, the market risk premium, is the B. It's the slope. So look here, if I write it like this, that's too big. So for a 1 unit change in the beta, the expected return needs to change by the market risk premium. That's what I said before. So let's see here. For a 1 unit change in X, Y has to change this amount. Though this amount is the market risk premium. And this amount is 1. So for a 1 unit change in X, Y has to change the market risk premium. That's the slope. All right, so what does this do for us? Let's solve some problems. So I spent some time teaching you about the market, about the risk premium, so you know when I talk about the market risk premium, what it is. So it's the premium, it's the incentivization of investors to take on the risky market portfolio, okay? To invest in the stock market. Okay, the security market line is always linear because we're going to combine a linear combination of risk-free and the market portfolio. And so it's still the case, like I talked about on the CML, the capital market line, I'm going to combine the risk-free rate, the risk-free T-bill, and the market portfolio here by lending the T-bill, in other words, buying one, and also investing in the market portfolio. So I'm going to end up here. When I invest partly in the market portfolio, but short sell T-bills, I can go here. So this is still the same concept as we talked about in the capital market line, but all assets are going to fall here on this line. Because why? Because of the very thing I just said, that for each level of, well, I didn't say all this, but for any level of risk, if an investor was prepared to take on a beta higher than 1 over here, then they can create this return by doing what? By short selling T-bills and investing in the market portfolio to get here. Investing the proceeds and their original investment in the market portfolio to get here. So the SML is always linear. The capital market line is for efficient portfolios, but the security market line is for any security and portfolio. As well, I'm going to demonstrate that investment projects can also fall there, right? The beta, if the beta is 0, but the standard deviation of returns is greater than 0, this is going to imply that the expected returns are just the risk-free rate. So what I'm saying is that beta of 0 will end up here. So any asset with a beta of 0 will end up here. What about beta of negative? What kind of assets would have a beta that's negative? So let's think about it in the way of the beta formula where you have this and this. So beta being negative means that the asset is negatively correlated with the market. So when the market does poorly, this asset does well. Do you know of any assets like that? Are you familiar with any assets? What about gold? Historically, when the market does poorly, it becomes even worse because people move to invest in precious metals. So precious metals would be here. Gold, silver, platinum. What other assets would have a beta of negative? Any companies that deal with precious metals or assets that that deal with companies that deal with precious metals, anything to do with precious metals industry. The other place we have is crypto. When the market does poorly, people go to crypto. Okay. So this line can go further back too. Guys, feel me? Like in Netflix, that's what they say. You feel me? You get it? Somewhat? So for the test, I'm gonna keep it really basic because I just stopped here, right? And I think for the next test, I'm gonna beef it up. I'm gonna do some more exercises on this. I have a lot of handouts I can give you, but I won't, obviously the test is next week. I don't want to give you too much more. But I'm going to give you some stuff to review for the final test, right? All right. So, oh, I feel like I already did this slide. Oh, I did. Okay. So if beta is 1, so if for any asset with a beta of 1, that means, so basically this relationship, this traces from risk to return. So if the risk is 0 and measured by the beta, if the risk of an asset is 0, it's going to have the same expected return as the risk-free rate. If the risk of an asset is 1, it's going to have the expected return of the market portfolio. So all assets will fall on here, just like others. So it could be a different asset, but it happens to have the same return as the market portfolio because its beta is 1. According to the security market line, or because of it, we can find and trace through the relationship and exploit the relationship of risk and return. So we've tapped it down and we've made it an equation, exploiting that trade-off. All right, so here's an example. We're going to use the capital asset pricing model. So for what you'll be given is the beta. What you'll be given is the beta. And with the beta, using the model that I will grab from here, it's messy there. I'll take it from here. Compute the expected return for A and the expected return for B. So try that. Let's take a moment to try that. Okay. So let's calculate. So what we're going to do is use this formula. And 4% plus the beta of A, which is up here, is 0.8, and the market risk premium, which we can calculate aside. 14% minus 4 means that there's 10% market risk premium. As long as you use percent and percent or decimal and decimal, you'll get the right answer. So that will give us the expected return to A. What did I do wrong? It's not 1%, it's 10%. And so you have, or you can write it as decimals. So 0.04 plus 0.8 times 0.1. Have to be consistent. So that's going to be 12%. Okay, and then for this one, we're going to mark up again above the risk-free rate with a beta now of 1.2. So more sensitive than the market returns. Again, the market risk premium is the same number, 10%, and this gives you 16%. So a 16% return for B and a 12% return for A. And this is based on the assumptions of the capital asset pricing model. So let's see, if in terms of the graph, A would have been so on our chart, A would be here. I mean, not exactly there, but to the left, because it has a lower beta than 1. And B would be here because it has a higher beta than 1. Okay, and then now what we're going to do is talk about combining them. So these are assets that could also be recreated by lending through buying T-bills and purchasing the market portfolio equivalent, and then ending up here and arriving at a lower beta than 1. And B similarly, well, it's going to be risk-free. We're going to short sell T-bills so we can invest towards the market portfolio and expand our opportunities. So we are going to end up here for B, or we could recreate B by doing that with short selling T-bills in the market portfolio. All right, so what about if we just take A and B and we combine them in a portfolio? Where will we end up? We should end up back on the line. So let's see, are we going to recreate the market portfolio or something around it? So that's what we do here. 60% invested in A and 40% in B. We should end up somewhere between those two on the SML. Here I calculate the expected return, 13.6%, And that's just using, because of, remember back, this is taking you back to the portfolio mean and standard deviation. Now this is new. What about the beta? The beta of a portfolio is just the weighted beta of the assets. So look at here, we're going to end up at a beta less than 1, but very close, with an expected return between those two assets returns of 12 and 16%, because that's a linear combination with weights less than 1. We could also get the expected return using the capital asset pricing model. So we could have calculated the beta, weighted beta first, put it into the capital asset pricing model, and found the new portfolio. And where will it be? It will be, P will be here. With one, like 0.96 beta. That is too thick. Okay, I only have someone here and I'm not sure who it is. I think it was Kevin. I think I saw the name earlier. So from here, you have some problems to solve. And this is the end of the notes, but you have various exercises I left for you to work on, and you could also try and work on the ones. Well, I'm gonna add a few. I'm gonna add a few exercises, and I'll upload this document and I'll upload this video. Okay. So are we good? You're gonna look at that? I should try and fix this. I'm gonna try and fix this. Amazing, I never noticed that typo. It's not a big deal really, but if somebody tried to make calculations, they would be very frustrated. Okay, so we're good, we're gonna go. So let me know if you have any questions, you can text me. It's really hard for me. I cannot seem to broadcast from Zoom. I mean, from the classrooms. It's terrible. I don't know. I'm gonna try and fix it today, but it's really hard for me because I'm just using the chalkboard, and it is just review in there. It's like a review class, but you're gonna have to come to participate. I'll try, but I can't guarantee on the board. It's too hard. I can't do everything. But I will try today. I'm gonna go see about what's going on in those classrooms with my equipment. I don't really like taking all my equipment with me there either, because I just don't like it, lugging it around and then putting it into the wall and not sure what's gonna happen. So but I will just be doing review there and exercises and answering questions. So try and make it. Okay, I'm going to sign off. And if you want to talk to me, just text me. Bye.